So we had finished up last time with a couple of examples talking about how you might go through and talk about some of these hypothesis tests that we had talked about. Again, want to just give you an example. This is, I don't want you to cut and paste this. I don't want you to sort of use this as any sort of template, but what I want with these is to give you a sense for what a comprehensive interpretation might look like, knitting together some of these different pieces and parts, right? It's a lot easier if we just want to give it things an up or down vote based on whether or not our p-value exceeds 0.05 or not. But again, if you think about that Wilkinson article talking about needing to come together, bring multiple sources of information in to start talking about things in a way that's more meaningful and insightful and things. So here, in our first version of our example, we had found a statistically significant effect. Again, we see our confidence interval for our population value doesn't contain our expected value under the mean, which was, what was it? What was our expected value? 80, all right. So this doesn't contain 80, right? Our interval estimate is saying that based on the data that we've collected, we would expect plausible values of population average for people taking antioxidants ranging from anywhere from 84 to about 100. 80 is not a value that's consistent with our estimate, right? So we already know that we're going to reject the null hypothesis. If we go through, run a formal test, we get a p-value. If we take a look at for a test statistic of z equals 3, the likelihood of having of drawing a sample from a normal population having mean of 80 is very, very small, right? Again, so we're using this. We're saying that this falls beyond our critical value. We're going to reject the null hypothesis and which suggests that it's likely that these data were drawn from a population who had a average cognitive functioning score that's higher than is typical of just the older population in general. Okay, so I wanted to bring all this stuff together. This one, on the other hand, population value or value average score in the population of general older adults more generally of 80 falls right in the middle of our interval, right? That population value or that estimate is consistent with the data that we've got, and so here we're going to reject the null. And if we reject the null, what are we saying when we reject the null, Layla?
That we've seen and observed, or we've observed an effect.
Yes, I'm sorry. Fail to reject the null.
Oh.
Yeah. Well, what are we concluding if we fail to reject the null?
That there's no observed difference between.
Okay. And I threatened Angeline with physical violence last year for that exact same interpretation. What's wrong with saying that there's no difference? Does our reject the null say that there's no difference, Kate?
No, it just says that you don't have enough evidence.
Exactly, right. We're agnostic. We're just saying we don't know, right? There could be a difference. There might not be a difference. We just don't have enough evidence to say that there is. Think about this. If this helps you think about this in this way, let's say I run a study, right? And it looks like so Emilio runs a study, he gets a correlation between two of his primary variables of 0.32, right? But he's only got 25 people in his sample, right? And so is that correlation statistically significant? Probably not, right? But is Emilio saying that he fails to reject the null hypothesis? But in his mind, does Emilio say, oh, the correlation is actually 0 because I failed to reject the null hypothesis? No. What's Emilio probably saying? I need to get more people, right? And so this is an important thing when we're thinking about what we conclude when we fail to reject. It's that we just don't have enough evidence to say that there is a difference, right? So make sure that, thinking about this in this way in terms of power, and we'll talk about this when we get into some of the strengths and weaknesses of null hypothesis testing, being very clear and not saying that we accept the null or that we're saying that there's no difference, making sure we're being accurate in our interpretations there, okay? Okay. Any questions about what we've gone through up to this point? Okay. Let's do another example just to try and get us back into the swing of things, solidify some of this. So we're saying that ginkgo and ginseng thought to improve memory. So what we want to do is we want to have, again, we're giving a sample of 36 people herbal supplements for 90 days. At the end of the 90-day period, we'll complete standardized memory tests in the general population, mean of 80, standard deviation of 18. Experimental sample found to have a mean of score of 84. Okay, so in a sentence, what is the null hypothesis to be tested? Laura, can you take a shot at, in a sentence, stating the null? Give me a statement of the null.
That the memory test scores for people taking ginkgo biloba will be the same as memory scores for people using ginseng.
Okay, so this is just a one. This is just a one sample test. So we've just got. We're not having. So basically, we're just giving herbal supplements. It's a mix of ginseng and ginkgo and stuff like that. So again, we've just got one sample. We're giving them herbal supplements, looking at their standardized memory scores, and what we want to know is, does using do herbal supplements increase presumably cognition, memory scores? So what would be a statement of our null hypotheses?
That people taking ginkgo biloba and ginseng would be equal to the population
Okay,
on memory scores.
cool. Almost there. What else can we add to this to make it just a little bit more precise, at least for this class? Yeah,
Say
John.
that there would be no difference between the scores.
Okay, yeah, we could say that there's no difference. Again, what we want to be thinking about, right, is in terms of populations, right? So if I'm talking about the general population of people and they have an average score on this exam of 80, right? What's the population that I'm wanting to infer something about, Nick?
Population in general would be anyone who would take the memory test.
Okay, right. And who am I interested in? Who's my experimental group here?
Those who take the herbal.
Right, right. And so wanting to work this in, and again, it can kind of be a mouthful, but it's a complicated task, but I want you to do it because I want you to be thinking about population stuff as opposed to sample stuff, right? And so what you might say is that the average memory score for the population of individuals taking herbal supplements is equal to 80. Okay? Because we're identifying, so we're not just, so we've got a sample of 36 people, but do we care about that sample of 36 people? Amanda?
No, we
No.
care about the population.
Care about the
They
population,
generalize.
right? And so we're saying that if we give these people consistent herbal supplements, these people are now, they were part of the general population, but now they're the part of the population that represent people who take herbal supplements regularly, right? And so our statement of the null hypothesis is going to be that the average memory score in the population of individuals taking herbal supplements is going to be equal to 80, just because we don't even have to get into general population, at least in this, because we're just saying, we're just pulling that in, okay? Does that make some sense? Do people see how we kind of, Laura was on track, we just kind of tweaked this a little bit to specify the population of interest here.
And you just want to state it in just a statement like that.
Just in a
and
statement.
I'm saying, even though I don't know yet, that I'm going to say that after 90 days, these people will have the same score as the people that we already took.
Yep, and that's kind of inferred, right? I mean,
Right.
that would be a
Okay.
lot. You don't have to describe the method in your statement of the null hypothesis. It's just
Okay.
your prediction. It's the model that we're testing with this analysis. Okay. So we've got point one out of the way. 2, state the null and alternative hypotheses and statistical notation. I don't want to whip a marker at anybody. Used to have an ag teacher in high school that fired markers at people. I think that was illegal. All right. Statement of the null hypotheses is going to do mean of supplement users equals 80. Alternate hypotheses, mean supplement users not equal 80. Okay, it's pretty easy, pretty straightforward. Just wanting to put in notation what we're testing here.
Are they both HO?
Oops. That's my alternate. Thank you. Okay, so now what we want to do, calculate 99 confidence interval for mean memory score in the population of individuals using ginkgo supplements. Okay, what's the first thing I need to do? What do you think, Haley?
We defined your Z-score that relates to the 99% confidence interval.
Okay, and what do I need to get before I can get my Z-score? Or well, what do I want to do? What do I want to do first? Let's calculate my confidence interval.
Get your standard error.
Standard error, yeah, that I like starting with my standard error. Okay, what goes in the numerator of my standard error? What do you think, Layla?
I was just like mentally trying to remember the formula.
Yeah. Nick?
Your sample mean minus population.
Okay, not for my standard error. Numerator standard error? Standard deviation. All right. What's standard deviation of the population? 18. Okay. Over square root of my sample size, right? So I've got 36 people. All right. This turns out into nice workable math. What's 18 divided by 6? 3. There we go. All right, so we got a standard error of 3. All right. Now, what's next? Evelina, what am I up to next?
Now where do you want to calculate your Z-score?
Now I can, okay, and what's my Z-score going to be?
Is it 2.5?
2.58, right? So this is going to be my Z critical. We'll call it Z crit. Okay. And so with this information, now I can go through and calculate my 95% or my 99% confidence interval, percent CI. All right. This is going to be my point estimate. So what's my mean? 80 for my 84, right? So I got a score of 84 plus or minus my Z critical 2.58. That corresponds to my confidence level, right, for this interval, multiplied by what, Emilio?
It's going to be
What is it?
3.
3, right? My standard error. Okay. What do I get in terms of my confidence interval? Someone crank that out for me. What's my lower bound? $76.3, we'll call it 3, and what's my upper bound? 91.7. Okay. Quick note on rounding. Rounding is the bane of Angeline's existence. It's the bane of my existence. Trying to figure out if you made an error in your calculations or you just got weird rounding stuff. In general, when you're running through calculations, if you're just walking stuff down, round to 3 decimal places in your calculations. But then when you're reporting, kind of depends on, like this, probably doesn't make sense to report to 3 different digits because that's basically random noise at that point. If we're reporting test statistics generally report those to 2 decimals, p-values 3 decimals. Means kind of depends on what you're looking at, but just be careful with some of that rounding. But for hand calculations, make sure that you're rounding to 3 decimal places on stuff. Another thing too, make sure that you're not just taking it out to 3 decimal places here. It was 76.4 something, or 76.2 something. Make sure you're rounding stuff so that you're not just cutting things off. If you don't do this, then we have to go back through and try and figure out why your answer is slightly different than other people's, if it's an error, if it's because of rounding stuff, so. All right, but we end up here with a 99% confidence interval based on our data for plausible values of the population memory score for individuals taking these supplements, okay? So based on my confidence interval here, Layla, what do I already know about sort of my hypothesis test?
I mean, the range is pretty, 90 and 76 to 91, that's pretty big.
Okay, it's a pretty big range, right? What's going into this large range here?
Yeah, larger.
Okay, my standard deviation is kind of big, right? What's a bigger impact on my standard error? What do you think, Kabila?
It's a big sample size.
Sample size. So 36 isn't big, right? Well, technically it's a big sample, right, in terms of what we talked about. 36 is kind of still pretty large. What's the other thing that's making this interval large? Yeah.
Is it that it's a 99%?
It's that it's a 99% interval, right? Again, remember that what we're talking about, so the technical definition of our interval estimates is that we're saying over the course of sort of all possible samples that could be drawn from this population, our confidence level is the number of hypothetical intervals that would capture the actual population parameter, right? So if we were to do this an infinite number of times and create an infinite number of intervals, how many of those intervals would we, or what percentage of those intervals would actually capture the population parameter, okay? And so what if I want to do, if I want to increase the number of intervals that are actually going to capture my population parameter? How can I make sure that not 95% are going to capture the population parameter, but 99% are going to capture the population parameter?
Do you make your,
I make them bigger,
your range
right? You know, if I said that this was, my interval was 0 to 1 million, 100% of my intervals would capture the population parameter, right? What would happen if I were to compare this with a 95% confidence interval, Amanda?
Your range would be quite a bit
It would be
smaller.
tighter, right? Because I'm willing to accept more error, right? But if I'm sitting at 99, I'm giving myself a little bit more wiggle room, right? And so wanting to keep that in mind. So based on 99% confidence interval, Layla, and that's going to correspond to alpha of what? 0.01, right? Am I going to reject or fail to reject null hypotheses?
I'm leaning towards rejecting.
Okay. What is so? What's my point estimate? What's my value, reference value under the null? 80. Where does 80 fall in this interval? Is right in there, right? So already, I don't have to run a hypothesis test. I've got almost all the information. I've got functionally all the useful information I need to have based on this, right? Because I'm going to say, at least at alpha equal 0.01, I'm going to fail to reject the null hypothesis because my point estimate or my reference value falls in the middle of that, right? 80 is not a refuted value. If you said, I'm saying the average memory score for the population of individuals taking herbal supplements is, what am I saying it is? John?
Can you say that again?
So what is, based on the data that I've collected, what am I saying, what's my best guess for the actual average memory score in the population of individuals taking herbal supplements?
84?
84, this is my best guess, right? And so John?
Could be.
Could be, right? That's a reasonable answer. Based on the data that we've collected, 80 is a reasonable answer. It's not, is it as good as 84? not based on the data that I've got, but it's still within this range, right? And so because our null value is contained within our confidence interval, we already know we're gonna reject the null hypotheses. What's the only caveat here? Or that we're gonna fail to reject, right? But what's the one thing, what's the difference between this interval and our typical approach or our typical standards for reject, fail to reject? What do you think, Laura?
Critical region?
Yeah, right. I'm gonna fail to reject a null at alpha equal 0.01. At alpha equal 0.05, I don't know yet, right? So this is one of these things we want to think about. Okay. So questions about calculating our confidence interval, interpreting our confidence interval. You guys did a fantastic job, right? We know this is a pretty broad interval, right? So our estimate based on these data, not terribly precise at the 99% confidence sort of level, right? And at the 99% confidence level, or alpha equal 0.01, we know we're going to fail to reject the null hypothesis because 84 is a plausible value. Based on the data that we've collected, we can say, sort of based on a 99% confidence interval, our estimate of plausible lower bound is 76, upper bound about 92, right? All of those are unrefuted values, or values that fall within that interval are reasonable estimates based on the data that we've collected. Anything that falls outside of those values would be inconsistent with our model. Not impossible, but not likely based on the interval that we've calculated. Yeah?
Would our null and alternative hypothesis ever be, instead of equal to or not equal to, would it ever be less than or greater than?
Yeah, and so then we're talking about directional hypotheses, right? Directional hypotheses are controversial. What happens if we, I saw you smirking over there. What happens if we were to say, make this instead of, because in actual fact, we're not saying like, I don't know, it'll be sort of different one way or the other. What are we, based on our question, what are we expecting?
For this one?
Yeah.
We're probably expecting to go up.
We're expecting it to go up, right? And so what we can do then, if we're doing that, we take all of our critical region and put it in one tail, right? Which ends up making our critical value for a one-tailed test not 2.58. It's going to be something that's lower than that, right? But what's the problem with one-directional tests?
At that point, there's a lot of questions for you from like a reviewer saying you probably put 7.5% in that one tail instead of 5%.
Yeah.
So you can say equal, but if that doesn't work out, you can always change it. So
Yeah.
it's just an issue of changing.
Yeah. So for methodologists, this starts to become a controversial issue. So if I say I'm doing a two-tailed test like we would usually do, right? We got this is 1.96, this is 1.96 negative, positive. This is my critical region. I got 2.5 here, 2.5 here, right? In this way, if I go through and I test and I say, if I find something, my mean that I get from, or my estimated mean of the target population is high above my null value or far below my null value, I get to claim statistical significance either way, right? But maybe I say, well, our herbal supplements are supposed to help out memory. So I'm going to say I'm going to do a one-tailed test. I'm going to do, a two-tailed test. I'm going to do a one-tailed test, right? And so I want 0.05 all in one tail. Someone tell me what, if someone's got a Z table handy, what's the Z score, the Z score that corresponds with 5% of the distribution in the upper tail? Anybody have it?
165.
1.65?
Yes.
That sounds right. Right? So what did that do to my benchmarks for being able to claim statistical significance?
More possible?
It made it more possible, right? I sort of moved the benchmarks a lot closer, right? And so, but some people would say, yeah, right? Like this is, if I'm saying that herbal supplements should make people perform better, I'm not really, I don't have a non-directional test. I have a very directional test, right? Based on what I'm expecting. And so if they're going through and we get something that says my test statistic is 1.76, right? If I have a two-tailed test, I fail to reject. If I have a one-tailed test, I claim statistical significance, right? And their methodologists would claim that, like, if you have a directional test, then you should be specifying directional hypotheses, right? And letting people know everything that we know in terms of our theory and the model and everything suggests that scores in this population should be higher than the general population or whatever value we have under the null. And so we're going to specify directional tests, right? And there's a very strong rationale for that, particularly when we have problems with low power in almost all of our studies. This is, from a theory-based standpoint, a very good strategy. Okay, what's the drawback? Yeah.
So if ginkgo biloba and ginseng were to actually make memory worse, you wouldn't.
Yeah, right. If it makes it worse, if it makes it way worse, if I'm way out here, right? Turns out ginseng rots your brain and it makes you 4 standard deviations lower than the population mean. We're still not claiming statistical significance because all of our stuff is out there, right? And so there's the potential to sort of miss this. Now, if you're a reasonable person looking at your data, hopefully you would notice that and say, okay, we've got a whole different thing going on here outside of the statistical test, right? What's the other concern with a one-tailed test? From an applied standpoint.
Like more than people switching from a two-tailed to a one-tailed because of the data, or?
Yeah. There's suspicions about, like, I'm going through and I found something that was marginal, right? And maybe it's an exploratory analysis. I don't know. I didn't have any idea about what was going on or what would happen. But I found out that I have a marginal effect using standards for my two-tailed test. But if I switch it over to a one-tailed test, now all of a sudden I'm where I want to be, right? And then all of a sudden I'm coming up with post hoc justifications for how I expected all along that this was going to be the direction in which things were going in. And so from a reviewer-based standpoint, you're going to have a very clear and very strong rationale for why you're proposing directional tests, and state that at the very first. And when you're proposing your study, that's something you should do. You should say, everything says that this is the direction that the test should go. If it's in the opposite direction, I don't even care about that, right? A priori, based on all the research that's been done, this is the direction that this needs to go. And so I'm going to specify one-tailed tests for this. It's going to be a more sensitive test. It's going to be a more powerful test. But the problem is concerns with, because we can't run around and police everybody's integrity and things like that, the decision for the one-tailed test didn't happen. Like, oh, I forgot about this until I looked at the data, and then I remembered, oh yeah, I was going to do one-tailed tests, right? That's the issue with this. Okay.
Isn't that why they're pushing for pre-register studies on directional based stuff?
Yeah, I mean, experimental stuff, you folks have kind of a different sort of approach to things, and I think in many ways good if the execution was consistent on it, you know. But this idea that sort of pre-registering studies saying, you're kind of calling your shot. You're like, this is what I'm going to do. This is the methods. These are the people that I'm going to collect. This is how I'm going to analyze the data. These are the tests the hypothesis I'm going to check. And so whether it's good, whether I find effects or don't find effects, I want this to be published. This is an agreement to publish these data based on I have a strong study, testing reasonable hypotheses. Everything looks good, right? Now, Yeah, but not everything can be pre-registered, and sometimes some of our stuff is sort of post hoc in nature and things along those lines, but these are kind of the issues that come up. Hal does a really nice job of talking about directional tests and some of the issues with that. Again, I wouldn't prioritize that because we're going through a lot of this stuff, but if you really want to get in the nuts and bolts of some of these concepts that we're talking about, Hal does a phenomenal job, so. Okay. Yes?
When you're designing your own stuff, or your own studies, do you want to start with a 99% and then start rolling it back so you have that wider range, or like to me 99% means like the best,
Yeah.
but it also gives you the widest range, which maybe is not the best in this regard. Does that make sense?
Well, I mean, it just makes your threshold, because again, even with a two-tailed test, critical value for a 0.01 is going to be 2.58, right?
Right.
So it's going to be a harder thing to cross, right? And so if you were going to do something controversial and you want to be very sure, right? So you're doing marketing stuff, you have an ad campaign that could go a number of different ways, right? But I don't want to be just kind of sure that this is going to work. I want to be super sure. Maybe you set that a little bit farther and say, hey, I've got, sort of based on the data that I've collected, sort of I had a pretty intense threshold. Now, in psychology, our studies are always chronically underpowered. You're just shooting yourself in the foot there, right? Again, we're going to talk about type 1, type 2 errors. As I crank up my confidence level, or I sort of, which correspondingly brings down your alpha level, I may have less type 1 errors where I'm saying that there's something there when there's not, but I'm also cranking up, but I'm bringing down my type 1 error, but my type 2 error is going through the roof. Type 2 errors we'll talk about is something we should be more concerned about than we are, but we'll get into that stuff when we start talking about ins and outs of strengths and weakness hypothesis testing. Okay. Cool. All right. So we've got our 99% confidence interval. We've made some conclusions on that. But now what I want to do is I want to conduct a hypothesis test at alpha 0.05 and provide a conclusion. All right. So now I need to go through and run my my hypothesis test. So I'm kind of already ahead of the game because I've already got a lot of the pieces and parts that I need based on putting together this 99% confidence interval, right? And so what I'm going to do is I'm going to say, all right, here's my distribution of scores, and what's my alpha level? 0.05. So what are my benchmarks going to be? 1.96, right? Negative 1.96, positive 1.96, benchmark here, here, here. Now I need my z-score, right? So my z, or my test statistic. My test statistic is going to be, my sample mean is going to be 84 minus 80 is my value under my null, divided by my standard error. It's going to be 3. This gives me what? What's my test statistic?
1.33.
What's that?
1.33.
1.33. Okay. So I go through, say my z is 1.33. It's here. And so what do I do even at alpha equal 0.05, Haley?
You fail to reject.
I fail to reject. Okay. I fail to reject. And what do I conclude based on my fail to reject?
That there is no difference. There is not enough evidence. To
There we go. I about came across this table actually like this, right? Yeah, we just don't have enough evidence, right? We're not saying that there's not a difference, right? Kate, if I were to have a sample of not 36 but 500, would that 4-point difference likely be statistically significant? At 500 people?
Oh, yeah.
Yeah, right? I mean, we can do that real quick. What's 18 divided by the square root of 500?
0.8.
What is it?
0.8.
0.8? So instead of 3, 0.8, right? If we take 4 divided by 0.8, what do we get? 5? Yeah. Now I've got a z-score of 5. That's way out there, right? Okay. Now, what would be my conclusion if I had a z-score of 5?
We would then.
We would reject the null hypothesis, right? So again, we're not saying that based on, all we can say based on the null hypothesis is based on the data that we've collected, we can't say that there is a difference or there's not a difference, right? The difference of 4 points between our sample estimate, the population estimate, it's 4 points. I just don't know if that's 4 points because the population of individuals taking herbal supplements is sort of actually, sort of just a little bit, not a lot, but the average memory score is about 4 points higher than we would expect from the general population, and that's a real thing, right? Or whether or not that average memory score of the population taking herbal supplements also is actually 80, and the 4 point difference I found here is just sampling error. It's just due to sort of random fluctuation. Okay. Remember our test statistics. Always think about these in terms of the difference that we saw, or the difference that we would expect just based on random fuzz and sampling stuff, right? But this is important. Why we shouldn't be interpreting null results as there is no difference, or there is no effect, or there is no relation, because if this difference stays the same and we crank that sample way up, then it's very clear, right? Now we could crank the sample up and this difference goes down to 0 because we actually don't have a difference between these population values. We just don't know. Okay. Questions about this or how any of this stuff goes together? People feeling more comfortable with interpreting some of these hypothesis tests? Cool. All right. So, a little preview of this, but we'll review it real quick here. The thing about different types of error, different types of mistakes that we can make in our statistical procedures. First type of error is type 1 error. This is when we reject the null hypothesis when the null hypothesis is true, right? This is us claiming that there's an effect when there is no effect to be had, right? We found some difference that's due to just random error and variation, and we're saying, huzzah, we've got something here, right? You know, historically we think about type 1 error as being associated with selecting an extreme sample. If my sampling distribution looks like this, and my actual population mean is equal to 100, right? Is it possible that I could get a sample with mean equals 120? Yeah, it certainly is, right? Does this mean it's a bad sample or that I did something wrong in collecting it? Not necessarily, right? It's not going to happen a lot, but every once in a while I'm going to catch something way out on the margins, right? And I may not recognize that it's way out on the margins, right? This whole replication crisis that experimental folks are struggling with, not that we don't have our own replication issues, it's just we haven't gotten as worked up about it in clinical stuff yet. But you can think about this as type 1 error, right? So someone somewhere got an extreme sample on a weird effect, published it, it became part of the canon, never to be replicated again, because every time you go through and run this study, you're getting something that's much closer to the mean, which is boring because there's nothing there, right? And so this would be what we would be talking about in terms of type 1 error. Me getting a sample that's just happens to be way out on the margins, but if we were to do this again and again and again, we're claiming an effect even though in actuality there's no sort of difference between our population estimate and sort of the value on set in our studies to try and manage this type 1 error. Alpha equals 0.05. We're basically saying a 1 in 20 chance of claiming an effect when there is no effect to be had. Okay. Alpha 0.01, rejecting the probability of obtaining the data assuming the null less than 1%, a 1 in 100 chance. Right? So again, what we're doing with controlling our alpha is kind of tightening the screws on how willing are we for someone to come out with a study that says, yep, there's an effect here, yep, there's a difference, yep, there's a relation, when in actual fact, it's not. We just happen to catch something out there on the ends. Now this can be because you got a funky sample that's not representative of anything, but it can be just one of those things that happens, right? It doesn't happen very often, but someone's got to win the lottery, right? Maybe it's you in your study, and you get to build a career on something that is not actually the thing, right? Questions about type 1 error? All right, so again, setting thresholds for our z's, alpha equal 0.05, 1.96, or alpha 0.01, 2.58, alpha 0.001, 3.29. These are values that are probably good to have memorized just because they come up when doing some of our screenings and things along these lines. But essentially what we're doing as our alpha level is getting lower and lower, we're just making those goalposts farther and farther out. It's making it more challenging to claim significance as we increase our alpha level. All right, type 2 error. This is when we fail to reject the null hypothesis when the null hypothesis is actually false, right? The actual population value in our sample isn't equal to the reference value. It really is different, right? But we don't have enough data to claim an effect, and so we reject the null hypothesis even, or fail to reject the null even when the null actually is not actually correct, okay? Here we're saying that there's no evidence for effect, or we don't have sufficient evidence for effect or a relationship in the population when there is one. This is associated with insufficient power, okay?
What does that mean?
It means that if I have an effect that's small, right, I find that the difference between group A and group B is real. If I looked at the difference in population A, or at the mean in population A and the mean in population B, those hypothetical values, the ones we can't measure directly, but in theory they are different. They're not different by a lot, but they are different, right? But if I try to detect those differences with samples of 15, 20, 25, something like that, I might keep finding the same difference, but I just don't have enough. And so it's not, I don't have, my standard error is too big, right?
Okay.
And so what I'm going is with these small sample studies, I'm consistently failing to reject the null hypotheses, even though in actuality, the population is different. So in this example over here, Amanda, right? With 36, did we fail, what decision did we make?
We failed to reject.
We failed to reject the null hypothesis, right? But as soon as we cranked up the sample, what did we do?
We rejected because it went way out of bounds.
Pretty easily rejected, right? Again, the difference that we're seeing is the same, right? We didn't change sort of how the score we got in our sample. We just increased the sample size. And when we increase the sample size, Kate, what does that do to our standard error? Drives it way down, right? And where does our sample, where do we put our standard error when we're calculating test statistics, Laura?
We multiply by the z-score.
Yeah, well, in our test statistic, where does it go?
On the,
What part of the fraction?
oh, the
Denominator. Your standard error is down there, right? And so what happens to our outcome if we start dividing things by increasingly smaller values? Goes way up, right? And so this is what's driving. So if I find that the sample of, or increasingly finding samples of people taking herbal supplements are scoring about 4 points higher above the mean of what would be expected based on our population value, but I've got small samples, I might consistently reject a null over and over and over again, right? Or fail to reject a null. But if I get a much better sample, as my sample goes up, what does that do to the accuracy of my estimates?
It increases.
It increases, right? So it's not just like, oh, this is a 4-point difference plus or minus a billion. There's a 4-point difference plus or minus 0.3 of a point, right? And that's creating increasingly powerful tests. Now in psychological science, now marketing, econ, and things like that, power often isn't an issue because you're working with hundreds of thousands, millions of observations, right? But in psychology, when we're out going through collecting things, like, oh, I'm going to test this effect, it's a small effect, and I've got a sample of 40. Who knows, right? And so this is an issue of power.
So to build on that, if you're limited by sample size, is replicating a way that you can start to reject the null because you ran it X amount of times even with that small size and you're consistently coming up with 4 points higher, or not?
Yes, and then we start to get into some meta-analyses, starting to move away from hypothesis testing and more into effect size types of stuff.
Okay.
And we'll get there in a bit.
Okay.
Okay?
Thank you.
Yeah, no, excellent questions. Other questions about our type 2 errors? All right, so our type 2 errors, greatest concern, where treatment manipulation has a small but reliable effect. We're doing something in the lab. I'm coming in and I'm doing something. So Nick, you've got a manipulation, you're doing something with going through teasing and sort of jury manipulation, something like that. And it's shifting people's perceptions of guilt versus innocence a little bit, and it's doing it consistently, but it's small. It's not huge. It's real, but unless you have lots of people and have highly and well-powered statistical analyses, you're unlikely to detect that, right? So small sample size obviously is the big one, but poor measurement too, right? This is why it's so important to have good measures that are reliable and consistent, because if we've got just, oh, I made this measure up on my own, who knows? There's a lot of extra static in there that adds to your error. And then outside stuff, right? I've got research assistants, some of them are good, some of them are not. Some people enter the actual scores, some people enter random numbers, right? Layla's helping me out right now. We're going through our lab. We go through, for anything that anybody enters, we have them enter it twice. One person enters it one time, another person enters it another time, and we go through and cross-validate, see do we have any discrepancies. Again, trying to just crank down the potential for outside error, or Haley, you're in a study and you've got someone who's way off base. They're kind of doing their own thing and running people through the protocol, adding in a whole lot of external factors, right? So increasing your sample size, making sure you've got good, strong measurements, and making sure that you're running tight experiments and good, consistent protocols. These are all things that you're going to go through and shrink down your type 2 error. Sample size is the biggest one, but any of these things can start to impact stuff. So if we're looking at this, no effect, and in actual fact, this is what happens. There is no effect. The null hypothesis is true, and you reject the null hypothesis. We made a type 1 error. But if we reject the null hypothesis and the null hypothesis is false, then we're good, right? Fail to reject and the null is actually true, we're good. But if we fail to reject and the null hypothesis is actually false, then we have our type 2 error here. Okay? So just thinking about the different types of mistakes that we can make when reaching our conclusions with these statistical tests. Questions on this? All right. So one thing, so we talked a lot about underpowered studies. In psychology, underpowered studies are kind of a problem, right? But important to recognize that we can get into trouble with overpowered studies too, right? Amelia, what's the problem with our overpowered studies?
You run the risk of type 1 error.
Well, and we'll sort of get into philosophical debate with this, right? What we can do, and this is part of our null hypothesis test, is we can start to make a big deal out of stuff that means nothing, right? Maybe you've seen sort of people who've done these types of demonstrations. On a big enough sample, I can determine across the United States that drowning deaths are correlated with the number of Nick Cage movies made in a year, right? If I'm looking at samples of 10 million, that's gonna pop up, right? And so from our, and that probably is a type 1 error. I don't know, maybe there's probably not a real thing, but as we start to increase just based on our precision, right, as things get tighter and tighter and tighter, what we might start to do is saying, oh, sort of this is a deal, this is a big thing, when actually it accounts for such a small piece of anything. Yeah, statistically it's significant, but based on the effects, it is something that's even reasonable to talk about or care about at all, right? And this starts getting into Neal's crud factor when we're saying everything's related to everything, right? If we get sort of precise enough, right? And so we'll talk about some of that stuff. So again, one of those things to be aware of is you're reviewing research. If someone has a sample of 500, 1,000, like 1,000, 2,500, and they're making a big deal about the fact that something's significantly correlated, if you look and find that correlation is, 0.03, might want to sort of, that should go through and start to temper your enthusiasm that something was correlated at p equals 0.049 in a sample of 5,000, right? So wanting to know how these things are working. Cool. All right. Questions on our null hypotheses test, what we've been doing up to this point? All right. So the question is this a reasonable procedure? So this is what we do. Is this something that's a useful thing to do? Are we getting reasonable inferences? Are we inferring things about our universe in a way that makes sense based on the steps that we're using here? Okay. And if we look through methodological literature, people have serious reservations on this whole approach to analyses and drawing inferences, and have for a long time. If you go down through, read some of these articles, Meal describes null hypothesis testing as a potential, a potent but sterile intellectual rake. Believes in his merry path along a train of ravished maidens, but no viable offspring, right? So we've done a lot of stuff, we've done a lot of things, we got nothing really to show for it, right? This naked emperor has been shamelessly running about for a long time. I hear and argue that null hypothesis testing has not only failed to support the advance of psychology as a science, but also seriously impeded it. These are strong words, right? For our basic approach to science, right? It's saying the whole thing is a friggin' sham if we get into the nuts and bolts of stuff, okay? And so, even though like these techniques, these things that we're working through, this is the basis of what we do. This is the basis of the epistemological basis of our knowledge. Like, how do we determine that there's a real effect or a real thing going on here? Widely misused, right? I think about this as like just psychologists running with scissors constantly, just all over the place, right? People who, perhaps not through fault of their own, just don't understand the basic limitations of what we're doing and what our tests actually are saying. And so this whole procedure, we go through, and I've given you some papers to read, questioning both the methodology and conceptually what we're doing with our tests, right? So if we think about criticisms from a very, anybody in here like a philosophy major or take philosophy class? Okay.
I had to.
You had to, some philosophy stuff, right? From a basic philosophical standpoint, like how do we know things, right? Basic logic, problems with the fundamental logic of null hypothesis testing. So our question that we would like to know as scientists is, given these data, what's the probability that the null hypothesis is true? So based on the data that we've collected, what's the likelihood that the null is actually the case, right? What we actually get when we're testing in our null hypothesis test, the question that we're actually asking is, given that the null is true, what's the probability of these data, right? So what I'm saying, what I would like to know is, I've run a study, right? Based on the data that I've had, what's the likelihood that there actually is nothing going on, right? And if that probability is low, then I'm saying, well, there must be something going on. But that's not what we're doing with our tests. What we're doing is we're saying, assuming that the null hypothesis is true, assuming that there is nothing going on, what's the likelihood that I would, the probability that I would obtain the data that I have? Assuming that the actual population mean is 100, what's the likelihood that I would get a sample of 120? Okay. Now these things seem like they're sort of the same thing. It seems like semantics, but very, very quick and very easy sort of evaluation of this logic finds that where this starts to break down, right? So if we were talking about absolutes, then we're fine, right? So if the null hypothesis is true, these data cannot occur, right? These data have occurred, therefore the null hypothesis is false, right? That makes sense, right? But what we do is, if this is what we're doing, this would be fine. But we're not saying if the null hypothesis is true, these data cannot occur. We're saying, well, if the null hypothesis is true, these data are unlikely to occur, right? And so these data have occurred, therefore the null hypothesis is unlikely to be true. This is kind of what we're doing. So we've taken something that's an absolute, and we've added some probability to it. This is fine. This starts to become problematic. So we say if a person is an American, he or she is unlikely to be a member of Congress. That's true. This person is a member of Congress. Therefore, he or she is unlikely to be an American, right? So it's a silly example, but it's sort of from a basic logic of how we're working through stuff. So here, we're fine. If this statement was, if a person is an American, he or she cannot be a member of Congress. Now, that's not a true statement, but if it was, this person is a member of Congress, therefore this person is an American, right? If we're working at absolutes, this is fine. But as soon as we add fuzz into the mix, which is what we're doing with our hypotheses test, we can very clearly start to put together examples that are absurd, right? And we don't want, if we have something that's our entire foundation of our science, that we can easily poke holes in something as simple as this, right? Cohen refers to this as the illusion of attaining a probability, right? So we're saying that, if the actual population value is 100, then these data would be unlikely, right? Fair enough. But we found these data, and so then we say this is not unlikely to be true. When we start to get fuzz and probabilities in there, instead of working with absolutes, we start to have things break down. Okay. We also have problems with non-equivalent probabilities. So again, our scientific question is, what's the probability of the null, or what's the probability, what is the probability the null hypothesis is true given these data? That's what we would like to know. That would be great, right? But again, what we're asking with our hypothesis testing, with our statistical analyses, what's the probability of these data given that the null hypothesis is true? And so if we take a look at sort of some notation here, we got the probability of the null given the data. That's what we want to know. And what we're actually asking is the probability of the data given the null. Sort of reciprocal, we're just kind of flipping this on its head, but these two aren't the same. They're not interchangeable from a logical probability standpoint, right? So again, and this is a device that's often used in logic, rhetoric, and things like that, right? If we just, okay, well, fine, let's just start giving examples as this and see if they start to break down, and they do very quickly, right? The probability that you speak English if you attend this class, the probability that you attend this class if you speak English. These aren't reciprocals of one another, right? And so again, what we want to do is we want to reject the null in an effort to conclude that the null hypothesis is unlikely based on the data that we've collected. But if we're going to do this from a mathematical standpoint, this is when we get into Bayes factors and probabilities and prior, posterior and prior probabilities and things like that. Has anybody worked with any sort of Bayesian analyses or at least heard of it? Right? Bayesian stuff is that we often don't have a good way to test the probability of the null hypotheses, right? If we did, we could use an alternative approach, but we don't, and so then things start to run into some problems. But again, treating these two things as if they were the same is problematic on a number of fronts. But we can start to look at this from from an empirical standpoint, not just from a linguistic device or approach. If we start working with things where we actually know the probability of things. If I know the posterior probability, before I study it, I know the probability of obtaining something, right? Then we can start showing how some of this null hypothesis stuff falls apart. So if we say the base rate of schizophrenia in the population is 2%, okay? We're saying 2% of people in the US will meet criteria for schizophrenia, right? And what I've done is I've developed a screening. 95% accuracy for positive diagnoses, 97% accurate for negative diagnosis, okay? So in notation, if we set this up, if we say HO is a person, in the case of normal, person doesn't have schizophrenia. H1, person has schizophrenia, right? And T is our positive or negative test. So the probability of a negative test, given that the person doesn't have schizophrenia, 97%. Okay? Probability of a positive test, assuming that someone does have schizophrenia, 95%. Clinical people, are we excited about this test? We have 95% or 97% specificity, or excuse me, 95% sensitivity and 97% specificity. Are we excited about this? Yeah, Evelyn, why are we excited about this?
It's a really high probability.
Yeah, because it rocks. Like, this is a great test, right? This is fantastic, right? We're super jazzed about this, right? And so, what we can say is the probability of a positive test then, given the null hypothesis, so the probability of a positive test in a normal case is going to be about 0.05, okay? This is a rare thing, right? So, to get a positive flag on a negative case, we say the probability of this is actually having about 0.05%. So within null hypothesis testing, right? Again, the probability of the data given the null hypotheses, right? This is our scientific question, right? So here are actual probabilities, but if we want to know, set up this is, we would be looking at this from a significance setting. We're saying the probability of the data that we've got, a positive test, assuming that the null hypothesis is true, is very low, right? And so in this case, we would conclude that the outcome is unlikely and that we would classify this case as consistent with the diagnosis, right? We would say it's unlikely for us to identify someone as having a positive test when they actually weren't, and then we're going to say, well, you probably actually do. Based on this test, we're saying that you have schizophrenia, right? Because this doesn't happen very often. People following me up to this point and sort of walking through some of these numbers?
So if you had a result that made you reject the null hypothesis, that person probably has schizophrenia because it shouldn't happen if the null hypothesis is true.
Exactly,
Okay.
right? So this is exactly what we're doing here, right?
Okay.
We're saying, well, this is an unlikely event if the null hypotheses were true, right? This doesn't happen very much when the null hypothesis is true. Therefore, this has happened, and so we're saying the null hypothesis is false. This is basically what we're doing with our null hypothesis test. And so from that approach, we would conclude that this is an unlikely outcome. We'll classify this person to have schizophrenia based on the test because we've got a very good test, right?
Okay.
But this doesn't address our question of interest, right? Our question of interest is not based on the data, what's the likelihood of the null. We want to know probability of the data given the null hypotheses versus the probability of the null hypotheses versus the data. This is what we're asking, or this is what null hypothesis testing is giving us. This is actually what we want, right? So the question here is, what's the probability of a negative test given a positive, what's the probability of a negative diagnosis given a positive test? Okay. And so the probability of a normal case given a positive test, right, is actually what we should be looking at. Before I diagnose Laura with schizophrenia, I should probably want to know what's the likelihood of a case, someone without schizophrenia having a positive test, right? Here we've asked what's the probability of a positive test given someone who doesn't have schizophrenia. That's actually not what we want to be looking at. Like if I'm going to go through with some intensive antipsychotics, I want to be really sure, right? This says it's very unlikely that we would get a positive test in a negative case. But what I want to know, what's the probability of a negative case given a positive test? And if we go through this is a much more complicated thing to go through. We need to know the probability of a positive or a negative case times the probability of a positive test in a negative case over probability of a negative case times the probability of a positive test in a negative case plus the probability of a positive case times the probability of a positive test in a positive case. You don't have to worry about this. I'm not going to make you do all this. But if you trust me that this is what goes on in order to answer this question, we go through and we see the probability of a normal case getting a positive test isn't actually rare at all. It's quite common.
For a false positive.
For a false positive, right? And so if we go through and we take a look and start to play this out, we can see where we get this, right? If I go through and I say the probability of a normal test with a normal case, 0.97. So someone has a calculator. I always want you guys to have a calculator. Linda, thank you. What's 949 divided by 979?
0.969.
Yeah, 0.97, right? So the probability of a negative test in a normal case is very high, right? And the probability of a positive test in a diagnostic case, what's 20 divided by 21?
0.95.
Yeah, right? So the probability of a positive case, or a positive test in a positive case is quite high. So we're working with columns, but what if we start going the other way, right? What if we say, so here we have 30 positive tests, so we have a total of 50 positive tests. 20 of those are with people with schizophrenia, but 30 of them are false positives, right? What's 30 divided by 50?
0.6.
Yeah, right? And so what we're doing with our basic logic, right, we are saying that the probability, we're saying, what we want to know as scientists is we're saying, what's the probability of the null hypotheses based on the data, right? Because that's a useful question. What's the likelihood of nothing going on based on the data that I've collected? But what we're actually getting with our null hypothesis testing is assuming the null hypothesis, what is the likelihood of these data? And these aren't reversible things, right? Here, we're talking about sensitivity and specificity. Here, we're talking about positive and negative predictive value, right? And so if we start to look at the nuts and bolts of the logic of this, it's likely that we're often saying, oh, we're assuming, or the inference that we're making is that this is going to be a rare thing that hardly ever happens, when in fact it's happening a great deal of the time. Okay. So this is an example straight out of Meal. Meal's going through and walking through this. Hopefully you've gone through and read the paper, or will go through and read the paper. Meal's a little dense. Who's jumped in on that Meal paper? All right. Okay. Meal's like a rite of passage. Like you I don't know if you're a graduate student, you should be forced to read them at some point. But it's brilliant stuff. It just sort of sit down and try and go through. Hopefully this helps make it through some of that stuff. Okay. Questions about some of this stuff that we've got going on? All right. So again, what we're doing with this whole case is demonstrating sort of some of the risk of using p-values to infer some truth about the null hypotheses based on the sample data. Because that's our scientific question, right? What's the probability of the null based on the data that we've got? We don't get that. We get the probability of the data assuming the null, but then we use that to try and make an inference about the thing we really wanted to do. It's kind of a bait and switch thing, and we can get into some serious problems without too much monkeying around with the data and see very clear drawbacks of this. So this is getting into the ins and outs and the logic, and again, this, if you've had one or more philosophy classes, some of these concepts are probably going to start to become familiar. But we've also got a more conceptual problem in that from a theoretical standpoint, we're putting a big amount of emphasis on determining whether or not the null hypothesis is false. But we can make a very, very strong argument that the null is always false. The null is never true, right? The null is always false to some degree. So basically you set up a straw man to test against, right? So from cont, it can only be true in the bowels of a computer processor running a Monte Carlo study, and then even a straight electron may make it false. So if the null hypothesis is always false, what's the big deal about rejecting it, right? We're holding up, so like, the difference between my population means of group A and group B is never going to be exactly 0. It's always going to be something, right? And if it's, we know that it's never going to be exactly 0, what's the point of asking whether or not this is going to be 0, right? It's kind of a ridiculous question, right? It's foolish to ask, are the effects of A and B different? They're always different for some decimal place, right? This is my favorite. Statistical significance testing can involve a tautological logic in which tired researchers, having collected data on hundreds of subjects, then conduct a statistical test to evaluate whether there were a lot of subjects, which the researchers already know because they've collected the data and they know that they're tired, right? This is an excellent example, right? We found with our sample of 36 that we failed to reject the null hypothesis, right? We don't have enough evidence to say that there's difference. But if we crank up, if we get enough people, if we maintain that same difference, it's going to be significant, right? And so functionally what ends up happening is our significant tests are just basically a function of did I get enough people to claim statistical significance. With unlimited time and resources, everybody's dissertations, everybody's theses would always be significant across the board if you just had infinite resources and time to collect an infinite number of data points, right? Which starts to beg the question, why are we making such a big deal about this if basically it's just a test of whether or not you have a big sample size, right? Some of the stuff that Mila is talking about in some of these papers, regardless of the specified theory, rejection of the null hypotheses is expected in the predicted direction half of the time, right? If group A and group B are never exactly equal, right? If one's always going to be bigger than the other one, then assuming that they are in actual fact, there's no sort of reasonable difference, half the time we're going to fall on this side, half the time we're going to fall on the other side, right? But we start to get rejection rates higher if the direction is plausible from multiple theoretical perspectives. So I've got a theory that's very novel and very interesting that I've came up that's very invested in, that says that watching my finger as I'm asking you to talk about your trauma over and over and over again is causing your neurons to realign, and that you're getting better and moving past your trauma because this eye movement is going back and forth. As you're talking about your trauma in extensive detail, the eye moving back and through is rewiring you so that you're going to move past your post-traumatic stress disorder. And turns out, if we test this, it's true. If you talk over and over again while you're watching my finger move back and forth and you're processing your trauma stuff, turns out that you do get better, right? And so I say, brain rewiring for the win, right? Problem with that is there's a lot of other things going on in that study and in that treatment that are more consistent with probably more plausible things than your brain rewiring itself that are causing things to happen and causing improvement, right? I can have a sweet space alien theory that I test, and if it happens to line up with other more reasonable theories, I'm probably going to find a lot of studies that are consistent with my basic understanding of space alien stuff, right? And so, as a consequence, probability that some incorrect or irrelevant theory is going to be supported in our null hypothesis test about 50% or more as our power starts to increase. Right? People see this sort of argument for null hypothesis is always false, right? And so basically what we're doing with our null hypothesis test is your check on if you've gotten enough we're not actually looking at effects, it's a test of how many participants that you've run, right? We're seeing how this is problematic from sort of a whole systematic approach to science. Okay. And then Neil talks about crud factor. Everything's related to everything, right? If I get a big enough sample, I can pull out all sorts of interesting relations left, right, and center, right? Because the relation between X and Y is never going to be exactly 0, right? It's never going to be 0.00000000 indefinitely. So if I get enough people, eventually that correlation is going to become significant, which starts to make me question why I'm doing this whole thing in the first place. If, hypothetically, if I would have captured 1 billion people, anything I tested is going to be statistically significant. All right. Other problems with our null hypothesis testing, it's sort of leaning in, sort of having us make dichotomous decisions on things that probably shouldn't be thought about in terms of being dichotomous. So in this scenario, we've got a pair of studies looking at the efficacy of a new intervention for insomnia. Based on a sample of 44, Lucky 2012 noted statistically significant advantage of the intervention relative to waitlist controls. So we got a mean difference of 3.6, standard deviation of difference score about 7, p-value 0.02. Okay. By contrast, No Luck 2013 failed to observe a statistically significant effect in a similar sample of 36 with a mean difference of 2.23, standard deviation of the difference about 7.6 with a p-value of 0.22. Okay. So Kate, are we saying that these studies have found completely different outcomes?
No,
And why not?
because the one that where you fail to observe significance is just saying that you don't have enough evidence.
Right, right. But what we often do is say, well, this study found something, that study didn't, and so the literature's in complete chaos, right? We don't know. Some studies have found something, some studies haven't. There's inconsistency within the literature, right? Which is what someone just at a glance might take this as. But if we go through, right, and take a look at what's actually going on, if we calculate our confidence intervals here, Luck found a mean difference of 3.6, 95% confidence interval 1.49 to 5.73, right? No Luck, mean difference of 2.23, 95% confidence interval negative 0.33 to 0.48, right? This is what we're looking at here in terms of these two studies, right? If we're plotting out the interval estimate. 0 here says that there's nothing going on, right? What am I seeing, Nick, mostly in this graph? If this is the confidence band for study 1, this is confidence band for 22.
There's a lot of consistency between them.
There's a lot of consistency and a lot of overlap, you know? Both studies found plausible, anything in this region here as plausible values for the true difference in my treatment versus my waitlist control, right? And again, even though No Luck 2013, 0 is a non-refuted value, where does 0 fall in that band? What do you think, Laura?
Very close to the limit.
Very close to the limit. And do we know, based on what we talked about in terms of confidence intervals, are all values within that confidence band equally likely? No. The stuff we get towards the end starts to get increasingly unlikely, right? So even though, based on our procedure, we say that a 0 difference between our treatment and our turning on the heat. Even though the difference between our treatment and our waitlist control, no difference is still within that bound. It's just on the edge, right? And so what we do if we go through, and this is where we start looking at things like meta-analysis and things like that, right? So I didn't find an effect. I can't claim statistical significance, but what was the difference that I did see? What was the confidence interval that I saw? And we start to see a lot of these start stacking up. We can say, well, nothing going on within that study.
Because of the overlap.
Yeah, because we've got a lot of overlap
Right.
here, right?
Okay.
And so if I were to look at this, right, just casually, I would say, well, who knows if this intervention works or whether it doesn't. But if I sit down and take a look more carefully, say, this looks promising, right? Again, both of these samples are quite small, right? But it looks like this is making some type of shift in terms of improvement. Now, whether or not a difference between my waitlist control and my treatment group of 2 to 3 points is useful and worth it, that's a whole completely different question. But it looks like there's nothing going on, even though based on just a reading of this was statistically significant, this wasn't, suggesting that we've got completely different things going on. If we actually look at the data, they're probably more similar than different in terms of what's actually taking place. Questions about this? Okay. And again, if we look at effect sizes, here we'll talk about those hopefully later on this afternoon. We've got a medium effect, a small effect, but they're still going in the same direction. They're still looking like there's something going on. This is going to be a small effect, and small effects are hard to detect in a sample of 36. But if you would have maintained that same effect in a sample of 60, what's going to happen? It's going to be statistically significant, right? So again, looking at some of the limitations of our statistical analyses and sort of making these yes/no decisions. Okay. Last thing I think we go through here, talking about bias against the null. What we do is tend to associate theoretical predictions with rejection of the null, right? So if I reject the null, then that's evidence for my study. But what ends up happening is we get one study that finds a significant effect and we publish it, and then we have that being part of our canon, but every other infinite number of studies, right? And this again is a big deal in experimental research right now. People for the past 30 years have been trying to replicate this one study that's in all the textbooks, and nobody can. But because they're not replicating it, they can't publish. And so this is all kind of going on in the background, that no one's ever been able to replicate this weird finding that we've built an entire theory around based on 1 or 2 papers that have come out of one lab, and who knows what's going on with that, right? If no one else can replicate the thing that you've done, that's a problem, right? And again, inflation of p-values and reported values are going to be likely misleading. I went through and I got a wacky sample that's way here at the end of the distribution, right? And so I'm saying, boy, I found this at p less than 0.001. But now everybody else is doing it, and everybody else is frustrated because we can't get this. Well, you can't get that because this is where your samples are coming from. Middle of the distribution where there's nothing going on, right? But our method of reporting results is based on publishing significant effects and not publishing non-significant effects. And so what ends up happening is all the non-significant studies don't get published, and even the stuff that does, we don't report all the things that we tried and didn't work out, and we just leave that out. And so all that stuff starts to lead to huge inflation and bias within our literature. So as a consequence, mean effect sizes in the literature likely are consistent with substantial positive bias, right? Here, even if in the population, right? So say, because effect sizes have a distribution just like everything else. Talk about some of the difficulties with that. But let's say the difference between population A and population B is associated with effect of D equals 0.15, right? Someone familiar with effect sizes, is that a big effect or a small effect? It's a small effect, right? And so with my studies that don't have a lot of people, am I likely to detect this effect? No, right? But out here, I just got a random sample with D equals 0.65, right? This one, am I likely to find that this is significant with small sample? Probably, right? So the one study that I've published has an effect size of 0.65. But this is an outlier, real effect, the effect is there. It's a real effect that we're talking about, but it's gonna take a big sample in order to detect this, right? And so this is why, based on, but this is a much more likely study to get published than something that's more reasonable around the middle of the distribution. And so what's going on is that when we look at our effect sizes, right, and we look at our literature and say, okay, this is the effect that I'm basing my power analysis on, well, you should probably know that that's a gross overestimate of the actual effect that you're looking at because of this bias, right? Alpha correction increases threshold for statistical significance and also probably contributes to this, right? So Amanda, you asked, well, why don't we just crank down our alpha and sort of just so that we're super sure? Well, we can do that, but then things that are probably more reasonable estimates of our effect aren't going to reach statistical significance. Only the stuff that is weird then happens to exceed our extreme threshold we've set, and then adding to the bias in the literature. So again, those lucky enough to meet increased threshold for a study, given further for a given study, further contribute to overestimate the population effect size. So as we start to put the screws down deck, we get preoccupied with type 1 error and set those goalposts so far out, probably what's going to happen is it's only those weird studies that exceed that and actually get there that far exceed the actual effect that we're looking at. And so now we say, oh, this is the population effect that we're looking for. And then we get really frustrated when none of our studies can detect it because the one study that we have or the two studies we have are way so far out of bounds of what would be typical because of our publication, approach to publication. So the result is that people who do focus on effect sizes end up with substantial positive bias in their effect size estimation. Furthermore, there's the irony that the sophisticates who use procedures to adjust their alpha for multiple tests, spawn for running in pools, are adjusting for a non-existent alpha error, thus reducing their power, and, if lucky enough to get a significant result, only end up in grossly overestimating the population effect size, right? And so this is the concern, right? Is we're worried about someone getting away with something and claiming an effect that's not there. And so as we start to increase our type 1, our restriction on a type 1 error, what we essentially do is throw our type 2 error through the roof. And those studies that do end up passing our exceedingly high threshold are probably not typical studies. Those studies probably don't have parameters that are representative of the what's actually going on in the population. And then we start to then have sort of a skewed understanding of what's actually going on in terms of effect sizes and things. So this is important in terms of, this is where meta-analysis comes in. Meta-analysis is going through and looking at effects and doing file group problems and saying, okay, in the published literature and the non-published, unpublished literature, what's going on? What's a reasonable estimate of the actual effect in the population? And if you look at meta-analyses, the effect, the aggregate effect is probably a good estimate of the population parameter, generally considerably lower than your favorite study that actually found it too. Because your favorite study is probably one of these ones way out here on the end of the distribution where everything else is following up more closely along the midline. Okay. So questions about sort of bias against the null, and this sort of goes into our approach to research and publication and things like that, and how we probably make this worse with some of the ways we handle things. All right.
Does that
yes.
mean that, so does that just mean that when you have those type 2 errors, then you end up generalizing onto the bigger population these obscure outliers?
Mm-hmm.
And so now when we're talking about a bigger population, that all of a sudden we're expecting 1% when it really is
Yep.
nowhere near that.
Exactly.
Okay.
Exactly. And so this is the only study that's been published here, and so everybody in this room is trying to replicate this, right? And so we're doing our due diligence, right? Well, we want to make sure we have reasonably powered studies, and so we're powering our studies to detect an effect of 0.65. But the actual effect in the population is 0.15, right? So if I go through and I say, wow, 0.65, I need to have 80 people in my study to adequately power it. Do I have an adequately powered study? No, because this isn't the effect I'm looking for. This is the effect I'm actually looking for. And so what's going to happen because my study's not adequately powered? I'm going to fail to reject, right? and we're just gonna keep doing this again and again and again and again. Again, one of these things that probably contributes to replication crisis. Not saying that everything that people people aren't able to replicate is not there, it's not an effect, right? There could be something there, it's just probably nowhere near the size of effect that was published in sort of the 1 or 2 studies that were able to detect it. So, thinking about criticisms of the null hypotheses testing that get people in problems is not recognizing what our system does and what it doesn't do. Okay, things our null hypotheses test don't provide: the extent to which the null hypothesis is true or false. Right. This isn't what this is. So it's not sort of my p-value is less than 0.001 so that my null hypothesis is way false. Right? Nope. That's a direct function of your sample size. Same thing. Well, my p-value is 0.55, so that means it's super true. Not the case. Okay. It doesn't provide an estimate of the magnitude of effect. We can calculate effect sizes. Null hypotheses aren't effect sizes. Does not refer to the probability of replicating observed parameters. Right. And again, did a study 70 academics. 60% of them thought that p equal 0.1 indicated a significant result would be replicated 99% of the time. Not the case, right? This p equals 0.01 says that assuming that the null hypothesis is true, the probability of obtaining a sample of this characteristic or higher is about 1%, right? But that doesn't say anything about replication, right? That has to do with effect sizes, a couple other things. And so, again, making strong interpretations about your p-values doesn't provide direct support for your theory, particularly if there are other theories that are consistent with the same predictions that you would make. There's no way to distinguish between that. And also, we reject the null for all sorts of reasons, right? Method effects, measurement effects, alternative hypotheses, things along these lines. And so, again, that statistical test tells us very little about our theory under examination. Things that we can tell based on our null hypotheses test: index of the probability of obtaining results as or more extreme than those observed under the data, assuming that the null hypothesis is true. So this is fine, but this often isn't what we're interested in looking at, right? What we're interested in is the probability of the null hypothesis given the data. What we get is the probability of the data given the null hypotheses. Then we get into back that whole situation. Okay? So appropriate conclusions: if we reject A is likely greater than B, or A and B are likely positively, negatively correlated or related, right? So we're just saying, if we reject the null hypothesis, we're saying that, well, these two things are likely associated, correlated, or related in some way. Fail to reject: direction of the actual difference or relation between A and B is uncertain. What is this getting at here? When we're saying the nature of the direction of the actual difference or relation between A and B is unclear. What's the assumption there? What do you think, Laura?
I would think since there's always going to be some difference, we
Yeah.
have evidence to see.
Yeah, right. So if I reject the null hypotheses, I'm just saying that I don't know what direction the relation between X and Y is. If I'm taking a conceptual perspective, I know the correlation isn't exactly 0. If I reject, I just can't say what direction it probably is, right? And I'm not saying from a conceptual standpoint, from a theoretical standpoint, I know group A and group B are never going to be identical. So if I reject the null hypothesis, I'm just saying I don't know what direction they're different in, right? Now, I wouldn't recommend trying to break ground in your thesis or your next publication with this, but you should know in the back of your head this is the true nature of things sort of as we're working through some of these tests. Okay, so reasons that we still have this, right? Communication, p-value is nice. P-value is a p-value no matter what type of statistics we do. It's a nice means of communication, translating across a variety of statistics. P-value doesn't mean the things that people often think it means, but if you understand what it does mean, you can go through and use that as a means of communication. At the end of the day, we have to have some means of dichotomous decision, right? We have to say, are we gonna say, okay, yeah, it looks like there's evidence for, evidence against, we're uncomfortable with ambiguity of continuous types of things in shades of gray. It's a nice standard, right? Our game might be screwed up, but at least we're all playing the same screwed up game, and so if we all know the rules, then I can sort of call you out if you've made some conclusions that might not be warranted, because I know kind of we're all working on the same system, and really absence of something better. You've got Bayesians who want to go through and will make some strong arguments about different ways we could go through and look at different types of things, but those analyses also have problems of their own. There's also a big training issue. This is the way we've all been trained to do things, and so we just kind of charge ahead, even though there are clear limitations. It's not great, but hopefully what you will get out of this class is understanding what we can infer from our tests, what we can't, and then be able to know that for your own research and then make reasonable interpretations about other people's stuff based on what they've done. So, suggestions. As researchers, considerable areas of statistical techniques, they can help us find our way to theories of some depth, but they must be used sensibly and heavily informed by informed judgment. So this is what thinking about what you're doing, why you're doing it, does it make sense? Pulling in not only your statistical analyses, but your methods and the logic. It's like, is what these people did, does this make sense? And using sort of common sense and background knowledge to make some conclusions there, right? Howell was saying, running a statistical test declaring a difference between statistically significant at p less than 0.05 no longer sufficient. In addition to running hypotheses tests, we need to tell readers something about the difference itself, about the confidence limits on that difference, and about the power of our tests, right? If I'm going through and I'm saying, well, I didn't find a difference between group A and group B, and group A has 10 people and group B has 12 people, I haven't said much about anything, right? Because I didn't have enough power to say anything about anything. I should probably make a note of that as I'm going through and talking with people, right? Within the context of null hypotheses testing, sensible conclusions are based on an intuitive weighting of such factors as p-value, power, effect size, number of observations, finding from previously related work, guidance from substantive theory, and performance of other models, right? So pulling all this stuff together, you know, people, I've had students in the past say, oh, you know, I like statistics because it's cut and dry, it's it's a basic procedure, and you get a decision at the end that's yes or no, and so that's really nice. Nothing could be farther from the truth, right? There's 1,000 different ways to do stuff, and you're going to come away with a large chunk of the force in you. You can use it for good, you can use it for bad, but at least you can go through and understand what's going on with these analyses, and hopefully being able to pull things in and be able to evaluate literatures critically. So recommendations, report your test statistics corresponding degrees of freedom and exact p-values. Knowing that p-values of 0.051 and 0.150 are not the same thing, right? People get really worked up about talking about marginal effects, but at the end of the day, p equals 0.049 is not any different than p equals 0.051. So, and you should understand that, right? Reporting descriptive statistics. Always report means and standard deviations, please. You'll be doing people a favor. Some graduate student down the road will thank you immensely if you've reported basic means and standard deviations, and knowing sort of what types of statistics to be reporting for what types of analyses. This is all going to be important for communicating information to people about what you've done. Augment null hypothesis testing with effect sizes and confidence intervals. We're talking about magnitude of effect, precision of effect, things along these lines. This can often be uncomfortable, right? I've got either a huge sample and I've claimed statistical significance, but my effect size is wicked small, right? It's itty bitty. I would like to avoid sort of drawing attention to that because I'm excited that I've got a statistically significant effect. But it's possible that that effect might be small to the point of being maybe not relevant for much of anything, right? Or I find a statistically significant effect, but my confidence interval is massive, right? I'm like, yeah, I just eked on the other side of zero with this, but huge imprecision what that actual population parameter is. It's uncomfortable, but it's important to go through it and communicate this stuff importantly. Reporting methods, software, using the calculation of statistics exactly the same way. reporting results of all relevant hypotheses tests, not picking and choosing what looks the best, and then being accurate, precise in your interpretations. All right, cool. Let's take a break. All right. I'm getting up and walking around with like cups. I just walk around with a giant thermos of coffee and just. All right. Okay. So up to this point, what we've been working with are tests comparing sample means to some known population mean and variance. Okay. These are our single sample z-tests, right? And all the examples that we worked up at this point, we're saying, here's my population, or here's my sample that I'm drawing from some novel population or some population of interest, and comparing the mean of that sample against some known population mean and some population variance or standard deviation. And so this is our single sample z-test. So again, as a reminder, let's say I know that the population of lab rats has a mean weight of 400 grams, a variance of 50 grams. I go through, take a sample of these rats and then give them some sort of treatment, right? These are now representative of a different population. These are the hypothetical population of treatment rats. And so based on the characteristics I find here, what can I make, what inferences can I make about the population of the treated rats relative to these known population parameters here, right? People sort of sticking with people kind of, yep, understand that, people good, okay. Problem is our single sample Z requires more information in order to conduct this than is generally available in our research. We need to know population standard deviation to calculate our standard error, but in most cases, we don't know what that population standard deviation is, right? And if we don't know the population standard deviation, we can't use a z-test. And so what we can do then, because our sample variance, right, unbiased estimator of a population variance, what we can do is we can use our sample variance as an estimate to estimate our standard error of the mean for our hypotheses test, okay? And again, this is going back to, remember when we went through and found that we have to change the calculation of our sample variance and our sample standard deviation a little bit so that it's an unbiased estimator of our population variance. What did we have to do when we were calculating sample variance versus population variance? What would we have to do? What did we do to that equation to tweak it a little bit? We subtract 1. We change the degrees of freedom, right? So we take that sum of squares divided by n minus 1 instead of n. And with that small adjustment, our sample variance is now a unbiased estimator of the population variance, right? So the issue with the z-test is that we often don't know, we can't run a z-test unless we know the population mean, the population standard deviation. We often don't know what the population standard deviation is, right? And that's a problem. But what we can do is we can take our sample standard deviation or our sample variance, and because that's an unbiased estimator of the population variance, we can just substitute that in to go through and calculate our standard errors. Okay? Everybody follow me here? All right. And we know that our sample variance is an unbiased estimator of our population variance because when we're talking about unbiased statistics, we're saying on average, the average value of a statistic across replication is going to be equal to population parameter, right? And so if we're thinking about our distribution of sample means, right? We know the mean is an unbiased estimator of the or our sample mean is an unbiased estimator of the population mean. Is the distribution of sample means? If we take the mean of all possible samples of a given size, we know that our expected value of the mean is going to be equal to the population mean, right? And because of that, we call the mean an unbiased estimator. Okay. Follow me up to this point? So, here's our population variability, right? Our sampling distribution of, this is our population distribution, and this represents our variability, right? And to calculate our sample standard deviation, our sample variance, we calculate our sum of squares. Sum of squares is just our sum of squared deviation scores. and we divide that that sum of squares divided by n minus 1. This gives me my sample variance, which is an unbiased estimator of my population. Okay. Problem is even though my sampling or my sample standard deviation is an estimator of an unbiased estimator of my population variance, problems arise with the sampling distribution of my sampling variance. Okay. So again, remember that we had to subtract n minus 1 because if I'm running samples, most of my samples are going to come from here. I'm not going to catch those outsides, right? So I'm not going to have an unbiased estimator of my actual population variability. But what I do is I decrease the denominator there a little bit, and that gives it just enough of a tweak so that that my estimator becomes unbiased, right? But just like we took our sampling distribution of the mean, right? And when we take the sampling distribution of standard deviation or variance, we run into some problems. So our sampling distribution of our variance is the distribution of variance estimates obtained from all possible random samples of a particular size that could be drawn from the population. So sampling distribution is the same as what we were talking about before, right? If I have, so if this is my sampling distribution, this is my distribution of sample variances of n equal 5 from a population with mean of 5 and variances equal to 50. Okay. What we find with the sampling distribution of our sampling distribution of our variance, we get a positive skew, and that positive skew starts to increase when our samples start to get small. So what are Amanda, what are the characteristics of, what's the shape of the sampling distribution of the means?
On this?
No, what do we know about sampling distribution of the mean? What's the shape of that distribution?
Commonly it's like a bell curve.
It's a nice bell curve, right? Mathematically, it turns out fine. Problem with the sampling distribution of variances is it's not normal. It's skewed, okay? And this skew gets worse when your sample size starts to get small, right? So if I'm looking at the distribution of all sample variances of size 100 that could be drawn from a population of scores, the distribution of sample variances is going to have some skew. But if I'm looking at the sampling distribution of all possible samples of size 20 that could be drawn, that sampling distribution of variances is going to be much more skewed off, right? And so here we see that in this distribution, and so this is a sampling distribution of variances with n equals 5. So this is a very small sample. But our population from which we're drawing from has a mean of 5 and a variance of 50, right? So if I take a look at the mean of my sample variances here, the mean of my sample variances is equal to 50, okay? But what ends up happening is it's 50, so it's unbiased. So the mean of all possible variances that could be from sample size 5 that could be drawn from my population, my sample variance is equal, the average of the sample variance is equal to the population variance, right? But this skew causes us some problems. So on average, a randomly selected value of my sample variance is likely to underestimate the population variance, okay? Nick, I see you nodding your head a little bit. Can you tell me why? So on average, the sample variance is an unbiased statistic because if I take the mean the mean value of this distribution of variances, the mean value of the variance is equal to the population variance. But what happens for any individual sample that I select?
For any individual sample, it depends on the sample size, but you're going to have a larger variance based on a smaller sample.
Well, and so if we have population or sample size 5, right? So this is a small sample. If I look at this distribution, if I just close my eyes and pull out a sample, where is that sample likely to fall?
Probably below what you're
Why?
you don't know.
Yeah.
Because we'd expect with a normal bell curve of the means that the sample should be closer to that mean.
Uh-huh.
And so when you do the standard deviation, it should be less. So I
Right.
mean, it should,
So if we just look at this distribution, where are most of our samples falling? To the left of the mean, right? This is a skewed distribution, right? We're gonna have my mean, or my mode, median, and mean, right, in the sample. My mean is getting drug out, right? Can I have a negative, value for my, variance? I can't have a negative, right? So 0 is the lowest I can get, right? And most of my samples, right, this is a frequency distribution, most of my samples are falling to the left of the mean of this distribution. Most of my samples are underestimating the actual population mean, right? Any individual sample, if I close my eyes and dig around and pull one of these out of the hat, I'm much more likely to get something over here than out here, right? And so for any randomly selected value or sample, our actual sample variance is probably going to underestimate the actual population variance. On average, the sampling statistic or my variance estimate is unbiased because the average of the sampling distribution is equal to the population value, right? But what ends up happening, and the reason this works, is I can only get variance estimates that are so small, but I can get variance estimates that are real big, right? And that skew starts to drag out the mean of that sampling distribution so that it's equal to the population parameter. But for any individual sample that I draw, any individual sample that I get is probably happening over here, right? And these are all sample statistics that are underestimating the actual population parameter. So if we've got a nice normal distribution, this isn't a problem, right? We're going to have some estimates of the mean that are going to be too big, some estimates that of the mean that are going to be too small. On average, everything's going to sort of cancel itself out, so we're real good, right? Here, any individual sample variance that we collect is probably going to be below. Now, there are going to be some that are way too big, and that skew is going to drag that out so that our sample statistic mathematically is unbiased. But for any individual sample that I collect, I put money on that it's going to be an underestimated actual population variance, okay? And so what ends up happening is if I'm underestimating my population variance, if I'm using my sample variance as a stand-in for my population variance, but I know that for any individual, any given sample that I pull, my sample variance is probably going to be an underestimated the actual population value. What's this going to do to my test statistic? It's going to make it too big, right? Why is this? Why are my z-tests, if I just use a z-test, why are my z-tests going to be too big? Any guesses, John? What do I use my variance estimate to calculate?
Say if like if it's underestimating, it's gonna be like smaller, like in the denominators, that would like increase your.
Exactly, right? So my variance is a core component of my standard error. And if my variance is too small, if my sample variance is systematically, if any given sample that I pull is likely underestimating the actual population value, my sample variance is too small, which means my standard error is going to be too small. Because my standard error goes in the denominator of my sample statistic, or my test statistic. My test statistic is going to be systematically biased. It's going to be systematically inflated. Okay? And this is all because my sampling distribution of my variance is skewed. It's not a nice normal distribution. And because of this, even though with the correction, my sample variance is an unbiased estimate. Because if I take the average of the sampling distribution equals the population value. But for any individual sample that I draw, it's likely to fall on this side and be an underestimate of the population variance, even though we've got these ones out here on the aggregate pulling it out. And so the reason we're concerned is that because I'm assuming that any random sample that I draw is going to underestimate the population variance, it's going to make my standard errors too small. which is going to make my test statistic too big, which is going to mean what in terms of my interpretations of my statistical test? What's the problem with this, Layla?
I'm sorry, could you repeat that?
Yeah, if my test statistics are systematically too large, what's going to be the consequence in practice if I'm just using just the Z test procedure and substituting the sample variance for the population variance?
Sorry, I didn't.
Yeah. So if my test statistic is systematically too large, what's that going to mean for my inferences?
Test statistic, what do you mean?
Like my Z test.
It's too large.
Am I going to reject too much or fail to reject too much?
I don't know.
It's a 50-50. Give it a shot.
Fail to reject.
Okay. So again, if my Z tests are too high, right? Again, thinking about okay. So for my Z test, I want my variance, right? But I don't know variance, right? But I do have a sample variance, right? And on average, my sample variance is going to equal this, right? But for any given sample that I collect, given that my sampling distribution, my variance is skewed, this is probably going to be smaller than it should be, right? So this is going to underestimate, right? And if my standard error is going to be my standard deviation over square root of this, if this is smaller than it should be, my standard error is going to be too small. And if my Z statistic is mean minus population mean over my standard error is smaller than it should be, my Z statistic is going to go up, right? If my test statistic is inflated, am I going to commit too many type 1 errors or too many type 2 errors?
Too many type 1 errors.
Type 1 errors, right? This isn't going to be, if sort of 1.96 is my benchmark, if my standard error, if using my sample variance as a substitute for my population variance, for any given sample, this is going to be too small, which means my standard error is going to be too small. My standard error is too small, it makes my test statistic too big. I'm going to more likely be claiming that I have found evidence of statistical significance than I would if I had an appropriate estimator of my standard error. So I'm going to reject the null too often. I'm going to make too many type 1 errors if I'm just using my Z procedure and my Z table and charging forward substituting my sample variance as an estimator of my population variance. Okay? You kind of sort of following me on this? All right. So, solution, right? This is a problem. So early on, people are saying, well, we've got this problem because the sampling distribution of our variance is, our sample variance is unbiased. The sampling distribution of this statistic is skewed, and so it's causing problems. So any individual sample that I'm going to get probably has giving me an underestimate of my actual population variance. And if I use that for my standard error, I'm going to get test statistics that are too large, and I'm going to be claiming things are different more often than I should, right, if I'm just using my Z procedure. And so one of the people to kind of crack this, gentleman named William Seeley Gossett, aka Student, okay? This guy, chemist for Guinness Brewing Company, and working with limitations of small samples. Remember, this distribution of the skew in my sampling distribution of my variance gets worse when I'm working with small samples. Gossett is working with beer, trying to go through and sort of do some systematic tests in terms of fermentation and sort of chemist stuff, and recognizing that, hey, I'm finding statistically significant effects more often than I should, and it's because I'm working with these small samples. What do I do? How can I go through and make an adjustment and correct? And so what the result of this was the formation of the t-distribution, okay? And students t, because I don't think Gaza was supposed to like get, have permission to go through and publish stuff, but he didn't, and so he just published. Gossett did was identified or defined students t-distribution, which is specifying the sampling distribution of the test statistic t using sample variance as an estimate of your population variance, okay? So again, what we've got going on is to calculate a proper z statistic. Z is going to be my sample mean minus the population mean over the square root of population variance over n. Okay? This is just your standard error right here. Okay? If I go through and I take the mean minus population mean over this is problematic. This is a different statistic, right? Because this is going to systematically underestimate this as a function of your sample size, right? And basically we've got a different distribution. If we just use this and then use our z curve and treat this as if it were a z, this is going to be too big, right? And we're going to reject the null hypotheses more than we should, right? And so what student did is he said, well, basically what we're doing, if we substitute this sample variance in for the population variance, we're not working on the z distribution anymore. We've got a new distribution. And this new distribution is a t distribution, right? And so with this t distribution, if we know what that t distribution is, we can start to make adjustments to correct for the fact that for any individual sample, our effect size, or excuse me, our sample variance is going to be an underestimate of the population variance. Okay? And so what Gossett did was sort of published this t distribution, which follows, sort of maps out the distribution of our test statistic, substituting our sample variance for the population variance. And what we got with our t distribution is actually a family of curves, all right, based on degrees of freedom. Now, a z distribution is a z distribution. Z distribution is one thing. Z distribution is always going to be the z distribution no matter what. But a t distribution, the specific shape of that distribution is going to depend on the degrees of freedom of your test. Your degrees of freedom of your test are going to be based on the number of people you have in your sample. Okay? And so as our t distribution is going to approach a normal curve as your degrees of freedom get to infinity, right? Because as my samples get larger and larger, right? So John, if my sample is 15, how much should I expect the bias of any individual sample to be for my sample variance relative to my population variance with sample equal 10?
It's like 15 compared to 10.
Well, if it sort of is more, is this going to be a big, a lot of bias or not so much bias if, for samples of 10 in terms of my sample variance as an estimate of my population variance?
It's going to be a lot of bias.
It's going to be a lot, right? As my sample starts getting bigger and bigger, let's say I get a sample of 100, 200, 300, 500, 1,000, right? How much is this getting a better estimate of this? Yeah, right? And so as our sample size start to increase, shape of the t distribution starts to become increasingly equivalent to your z distribution, okay? But as you get less and less degrees of freedom, right? Amelia, what am I expecting this to do?
Should go
Up, right? In terms of my bias, but what should I expect in terms of this number relative to that number?
the bias should go down.
Yeah, this is going to increasingly underestimate, right? And so what happens is with our t distributions, what we start to do is we get different critical values based on the degrees of freedom, right? And as we have lower and lower degrees of freedom, the shape of the distribution is such that we get, our test statistic has to get larger and larger in order to claim statistical significance. As our samples get increasingly large, as we start to approximate that z distribution, then critical values in our t distribution get closer and closer to the same benchmarks that we were using previously in the z distribution. Okay? So, sampling distribution of our t statistic for any given degrees of freedom. Our t statistic is the same as, in form it's identical to our z distribution. Basically we have our mean minus our population, our sample mean minus our population mean over the standard error. Standard error is just our sample standard deviation over the square root of the sample size, or sample variance over square root or sample everything, so it's just algebraic thing. But what ends up happening is as our degrees of freedom decrease, right? And our degrees of freedom are based on our sample size. As our degrees of freedom increase, our critical values become more and more extreme, okay? And so what we end up at lower sample sizes, lower ends, we get a greater threshold for our statistical significance. And so what this ends up doing is it ends up being a correction for our underestimate of the population variance and our reduction of our standard error based on using our standard, our sample sample variance as an estimate of our population variance. So I gave you guys a sort of a t test table there, right? Yeah. So grab that, take a look at that. So your T table here, it's not going to be like your Z table, which is identifying one curve. Your T table is going to be identifying and sort of looking at characteristics of a lot of curves, okay? And so let's say I have 10 degrees of freedom in my sample, right? And so degrees of freedom there in the left-hand column, I'm going to look down and find 10 degrees of freedom. And then what we're going to focus primarily on level of significance for two-tailed tests. But let's say I set my alpha equal to 0.05. Okay, Haley, for a test with 10 degrees of freedom, alpha equal 0.05, what's my critical value that I need to achieve in order to claim statistical significance?
2.23. 2.228.
Yes, 2.228, right? Okay. What is, if we were looking at a z-test, what would be my critical value at alpha equal 0.05? 1.96, right? And so what ends up happening with this t-curve, right? At lower degrees of freedom, our tests, our area under the curve, if we want to say, all right, we want 2.5% in one tail, 2.5% in the other tail, these tails get kind of thick, right? And so we have to go increasingly far out to section off 2.5 in one tail and 2.5 in the other tail. And what that ends up doing is setting our benchmarks farther out, right? But remember, the whole concern that we have with just utilizing our sample variance as an estimate of our population variance is we're worried that our sample variance is going to be too small. It's going to underestimate the population variance. And if we underestimate the population variance, what do we do to our standard error? Our standard error is too big or too small? Too small. And if my standard error is too small, what does that do to my test statistic? Makes it too big, right? And so with our t-test, what we can do is we can start plotting this out to say, okay, well, we know that our test statistic is going to be big, but then what happens is we just identify for this specific curve, for a test statistic with 10 degrees of freedom, this is the distribution of those tests, and in order to get 2.5% in the one tail, 2.5% in the other tail, these are the threshold we need to meet. So it's no longer 1.96, it's going to be 2.228, right, at alpha equal 0.05, right? Kate, what about for, again, say alpha is 0.05, but let's say we have 30 degrees of freedom. What's our critical value? 2.042, right? We've got more degrees of freedom, which suggests we've got more people in our sample, which suggests that our sample variance is probably a better estimate of the population variance. So we're gonna have less shrinkage in our sample variance. And so what we do is we start to, the test statistic in order to get trapped 2.5% here, 2.5% here, our critical values come in. What if we, sort of once we get to 100 degrees of freedom, Amanda, what are we looking at alpha equal 0.05?
1.984.
1.984, right? As we start to get 100, and so after that, right, the table just says, anything above that, we're just gonna say 1.96, right? And so what we get here is what Gossett did, is identified this family of t-distributions, right? And we're saying that, assuming that the null is true, assuming that there's no difference between in the sample and sort of this sort of population parameter, if we were to plot out the distribution of this statistic using the sample variance as an estimate of this, we get different shapes and different curves. And with every degree of freedom change, that changes that shape a little bit. And so for every distribution, or every distribution within this family, we're going to have a little bit different critical values depending on how many people we have in our sample. As our samples get smaller, our goalposts start to get farther and farther out, right? Because this is going to be increasingly smaller than this, which is going to make this increasingly larger. And so everything starts to balance out in terms of using our t-distributions, working through this stuff. Okay. People kind of see what's going on in terms of the corrections and sort of where these distributions are coming from. Okay. It's a lot of math, but again, I'm wanting people to go through and think about, so I'm not making you derive any proofs or anything like that, but just wanted to know from a conceptual standpoint why we need to, if we're using our sample variance as an estimate of our population variance, why we can't just go through and charge ahead and use our normal curve, why we have to go through and use a different distribution, because this is, again, assuming the null is true, assuming that there's no effect. If we were to go through and infinitely sample and calculate t-tests based on those samples, using the sample standard deviation as a plug-in for the population standard deviation, this is what that distribution would look like for, let's say, 10 degrees of freedom. And maybe this is what it looks like for 20, and this is what it looks like for 30, right? Looking at the sampling distribution of this statistic. And if we know what the distribution is, then we can go through and start assigning probabilities. Okay. Questions about this? Yeah.
So basically, the difference between like a Z and a T would be for estimating the population standard deviation?
Yeah. So again, for the Z-test is kind of our basic thing, right? Because it's like, okay, we're comparing some sample mean that I've got against a known population mean and a known population variance, which is a nice way to sort of get into this. But this is real life, right? I don't know what the population standard deviation is. I also don't know what the population mean is most of the time, but we'll get into that, right? But if I don't know what this population standard deviation is, I can use, or my population variance, I can use my sample variance as an estimate, but the sampling distribution of my sampling statistic, of my variance is skewed, and so that we've got some problems here. And so if I go through and run that curve, so basically, if I were to replicate a study an infinite number of times, using my sampling or my sample variance as an estimate for my population variance, the distribution of that statistic wouldn't fall on a Z curve. It'd fall on a Z curve. Now, if I have enough people in my sample, that T curve might look a lot like the Z curve, but we usually don't have a lot of people in our sample. We usually have less people in our sample. And so Gossett worked through all this to try and solve this problem of how do we go through and conduct appropriate tests of statistical significance when we're using, in cases where we've got small samples and we're using our sample variance as an estimate of the population variance. Okay. Yeah.
So, just by that statement, are you saying that t-tests are better for when you don't have as large of a sample?
Well, t-tests are going to be necessary almost always, because it's rare that we're using it, where that we're confronted with a situation where we know the population variance. If you don't know the population variance, you're in T-zone land, okay? The test is the same. You're constructing the test statistic functionally the same way. We just don't know what the population variance is. We got to use our sample variance as a substitute for the population variance. But when we do that, when we substitute our sample variance for the population variance, it changes the distribution of that test statistic, and it changes it over a t statistic. We can't just use that z statistic, because if we do, we're going to commit too many type 1 errors, because particularly with small samples, our test statistic is going to be larger than it should be. All right. So, quick. All right, you guys probably want to run out of here screaming. So, someone tell me what do we interpret this as? What is this here? Someone be brave. Anna?
Your sample error divided by the square root of your sample.
Right. And what is this statistic here?
Your sample error.
My standard error.
Standard
right?
error.
And can you give me a concept? So what is my how do I conceptually understand standard error? What is standard error?
Standard error is how any one person that you, or any one data point that you draw out of that group, how far it is away from the mean.
Fantastic, right? Within this distribution, right? This is how much fuzz I would expect to jump around, right? So across repeated samples, how much I would expect one sample mean to deviate from the next, how much I would expect one randomly select, on average, a randomly selected sample to follow from the actual population mean. So this standard error is, again, what I would expect based on just sampling stuff, right? So again, our test statistic is what we've observed versus what we would expect based on just sampling error, right? And as what we observe gets increasingly larger or smaller, increasingly greater than what we would expect just based on random variation, that cranks our test statistic up, makes it more likely that we're going to reject the null hypothesis. Okay? Fantastic. Yes. All right. Also note that our test a classic example of a leptokurtic distribution, right? Remember, kurtosis in general, looking at how peaked or how shouldery a distribution is, as our at T distributions with lower degrees of freedom, those distributions are much more peaked with kind of long flat tails. If there's more stuff going out in the tails, we got to get farther out in terms of capturing just the last 2.5%, the last 2.5%, right? So again, T distribution, classic positive kurtosis. Normal distribution, sort of nice and zero kurtosis. T distributions, peaked, and then with kind of thick, flat tails that go out. Okay. So if you want to ever get a sense for, what does positive kurtosis look like? Just look at a T distribution with low degrees of freedom. That's positive kurtosis. Okay. Oh. This is cool. This is from students' actual, one of the students' publications. They say, people unfamiliar with the term kurtosis, mesokurtic is having blah, blah, platykurtic. I myself bear in mind the meaning of the words, sort of the figure presents the platypus, second kangaroo, right? So we've got platykurtic here, leptokurtic, right? This is like, I don't know, I would encourage you all sort of for your next thesis to just hand some handwritten pictures in there and just be like, I would like to submit this as an example of kind of what's going on. But yeah, I haven't seen these sweet ass animal drawings in any articles lately. So, all right. So looking at our T distributions here, this is just a shot of your t-test that I handed out here. Again, what we're looking at here is trying to find what our critical value is, right? So down the right side, we have our degrees of freedom, level of significance. This is our alpha level for a two-tailed test. Probably not going to be working around anything here, right? But we're going to say 0.05, 0.01, 0.001, right? Here would be if we're doing directional tests, one-tailed tests, we probably won't worry about that too much. But what we're gonna do is instead of just saying, like with our Z statistic where we have our critical values of 1.96 plus or minus for alpha equal 0.05, for our Z tests, if we're substituting our sample variance for the population variance, what we need to go distributions, right? So depending on the on the degrees of freedom, we're going to be working with a different sampling distribution for that test statistic based on individual levels of degrees of freedom. So our t-tests are a family of curves as opposed to our normal distribution is just one normal curve. Normal curve is what it is. Okay. All right. So
How do you know
Yeah.
what your degrees of freedom is?
we'll talk about that.
Okay.
So our z-test structure to determine whether a random sample mean is likely to have occurred in a population with a known mean and variance. Okay. Rejection of the null interpreted as evidence that scores unlikely to have been drawn from a population with mean of equal to u. Right. So if I go through and with a z-test, I'm saying I've drawn a sample that has some characteristics, right? And I want to test whether or not it's equal to some reference value, and I know the reference mean in the population and the reference variance of the population. And so I go through and I take a look at, calculate my z-statistic, and if I find that the difference that I've seen in this sample is a great enough difference over what I would expect just due to random sampling error, what I'm going to do is I'm going to reject the null hypotheses. And I'm going to say that this is evidence that the scores that I've drawn from this sample, the population parameter for this sample is unlikely to be the same as it is for this reference value, because it would be unlikely, assuming that this population value is equal to whatever my reference value is, it would be unlikely for me to collect a sample with these characteristics, assuming that sort of these are the actual parameters we're working with in the population, right? So again, if I've got if I'm wanting to see if people who attend university have higher achievement scores than the general population, right? I can say, well, I know that the average achievement score on this exam is 100 in the population with standard deviation, equal to 15, right? And so what I do is I go through and I get a bunch of people, random or a representative sample of undergraduates at university, and I go through and I test their, and I get achievement tests with them, right? And I find that they have a mean equals to 106, right? So my question is does do undergraduates have a mean achievement score? Is the average achievement score in the population of undergraduates, is it larger or is it different than what we would expect based on the normal distribution of scores, right? And if I get a Z statistic that's large, right, I would say that these data would be unlikely to be observed if college students actually did have a mean achievement score of 100. And because these data would be are unlikely to be observed, assuming that undergraduates actually do have a true population value of 100, we're going to reject the null hypotheses and say then it's probably larger, right? If we don't, if we fail to reject, we say, well, we don't know if undergraduates are systematically higher achieving or lower achieving than the general population. We just kind of don't know, right? Okay. Now, when we're using our single sample test, this is when we're comparing a sample mean to some population value when we don't know the population variance. Population variance is unknown, right? And so our t-distribution corresponding to degrees of freedom, correct for the underestimation of the underestimation of the population variance because of that skewed distribution of our sampling distribution of variance, right? Particularly at small sample size, we get increasingly large bias, or expect increasingly large biases. Our sample size gets smaller. Threshold for significance, starts to become greater for smaller versus larger samples. And so we get these critical values for a single sample test outlined in our T table here. So factors influencing our test statistic, right? If we're working with the T distribution, again, T distribution, we're calculating our test statistic the same way we calculated Z. Not anything new or interesting going on here. It's still our sample mean minus the population mean over our standard error. Standard error is just our sample standard deviation over the square root of n, right? But things that will start to impact our test statistic is the difference between our sample mean and our expected value under the null hypotheses, right? Evelina, as that difference gets increasingly large, what happens to our sample statistic? It also gets large. All things being held equal, the more of a difference I find from my expected value under the null, I'm going to get a larger test statistic, right? Nick, what happens as my sample size increases? What happens to my test statistic?
Sample size increases, your standard error is smaller, and your test statistic will be
Test
larger.
statistic gets larger, right? All things being held equal, so my sample size goes up, my test statistic's going to go up, and my test statistic's going to go up because as sample size goes up, it's going to drive down my standard error. This denominator is going to get smaller, drive up my sample error, my test statistic, and also my sample variance, right? We often can't do much about our sample variance. Our sample variance is going to be our sample variance. One thing we can do is make sure that we're using good measures, strong measures that go through and are measuring things accurately, so that we don't have just extra static and fuzz going on and stuff. And so, Layla, as my sample variance decreases, what does that do to my test statistic?
Would it also go down?
It's going to go up, right? So I've got a smaller number here divided by, so if this is smaller and smaller, divided by a larger number, again, it's going to shrink down my standard error, and if my standard error is getting small, it's going to increase that, right? This is really kind of the least we can sort of do stuff with. But again, the main thing we want to do if we want to bump up our sample statistics is make sure that we have large samples. Large samples are going to drive down that standard error. That's going to be the biggest impact on your test statistics, all things being held equal. Okay. Questions about sort of drawing all this, putting all this stuff together? Okay. Quick word on degrees of freedom. Degrees of freedom, looking at the number of values in a calculation of a statistic that are free to vary. Okay. So let's say that this is a true statement. Okay. X plus Y plus Z is equal to 24. Okay. Laura, tell me what X is. What's that?
Could be a number of different values.
Could be anything, right? But tell me what it is in general. Give me a number.
4.
4. All right, this is 4. Evelina, what can Y be?
10.
What's that?
10.
Could be 10, all right? Does it have to be 10?
No.
Could be anything, right? But let's say it is 10. So X is 10, or X is 4, Y is 10, all right? Okay, what about Z? Can Z be anything? No, right? Z can be one thing, right? We've run out of your degrees of freedom. So here we have 2 degrees of freedom. We can pick whatever we want for X. We can pick whatever we want for Y. But once we have X and Y in place, Z's fixed, right? So this is when we're thinking about degrees of freedom, we're talking about parameters that are free to vary, right? In this equation, we've got 2 degrees of freedom, right? 2 of these, and it doesn't matter which ones, it can be Y and Z, it can be Z and X, it can be X and Y. We can there's an infinite number of possibilities. This could be 8 trillion and this could be negative 90 billion, right, if we wanted to. But as soon as we set those 2, that last parameter is fixed, right? And so in thinking about degrees of freedom and what this is kind of an abstract thing to think about, but from a statistical standpoint, this is what we're talking about. How much room do we have to vary, right? So in the case of our single sample t-test, we have 1 degree of freedom, and so our degrees of freedom for our single sample test is going to be 1 minus the number of people you have in your sample, okay? And that loss of degree of freedom based on our use of the sample mean to calculate our variance, right? So our variance is calculated as a function of the deviation of each score from the mean, right? Remember, think back to how we're calculating variance. We say, all right, so this deviation, this deviation, this deviation, right? But because the sum of your deviation scores has to equal 0, final value in that distribution is fixed, right? So if we're thinking down, and go back through and take a look at those slides where we talked about calculating your sample variance. So we've got a deviation score, deviation score, deviation score, deviation score, deviation score. Any of those deviation scores could be anything in the universe, right? But as soon as we get to all of them, to the last one, we know that the sum of your deviation scores has to be 0. And so that last parameter is fixed. That's where we're losing that degrees of freedom. And because we only use one variance in a single sample t-test, single sample degrees of freedom for our single sample test are going to be n minus 1. Okay. All right. We'll leave it at that. Nice work today. This was a lot of like heavy, like theory-based stuff to go through, and things that often you won't